Welcome to the Explainer. So today we're diving into something that is an absolute game changer for any developer trying to navigate this wild new world of AI coding assistants. We're talking about translating your architectural intent into literal, concrete guardrails. Why? To keep your system from collapsing while letting AI do the heavy lifting. It's all about using package-oriented software design to safely box in your AI.
But, okay, right off the bat, we've got to address the elephant in the room. How do we constrain AI from making dangerous system-wide changes? Seriously, it's the critical question right now. We all know AI coding tools are insanely fast, but without strict boundaries, that speed is honestly a little terrifying. If your AI suddenly decides to refactor a core class, it can wreak absolute havoc on your codebase, accidentally snapping dependencies across entirely unrelated features. We need a way to harness that speed, but do it safely.
All right, let's look at the agenda for today. We're going to start with why AI needs guardrails, then define the package boundary, and look at the public inbound surface. After that, cross-package collaboration, testing and backward compatibility, and finally, we'll wrap up with the ultimate AI advantage.
Section 1. AI needs guardrails, controlling the chaos.
You see, to actually solve this problem, we first have to recognize that ambiguity is the ultimate enemy of an AI assistant. If an AI doesn't know exactly where a specific behavior belongs, it just guesses. And guessing leads to total chaos. So the foundation of controlling this chaos is a classic principle: separation of concerns. In our context, this means splitting your system into packages, where each package owns exactly one coherent capability. Now, the key here is that a package shouldn't just be some random folder of loosely related classes. No, it needs to represent a highly specific responsibility. We're talking orders, inventory, or payments. By making this ownership crystal clear, we instantly narrow down where the AI should even be looking to make changes. So when a change is requested, the very first architectural question is always, which package owns this concern? Boom. Answer that, and you've instantly constrained your AI's workspace. Moving right along to Section 2, defining the package boundary, the black box.
Once we know exactly what a package owns, we absolutely have to enforce its borders. Think of the package boundary as a locked, closed room. Up at the top, you have the surface interface. This is literally the only front door into that room. Everything else, all those interconnected internal classes humming away inside, they're completely hidden from the outside world. Everything inside that boundary belongs exclusively to the package.
Now, establishing this boundary creates two very distinct realities. Inside the room, total internal freedom. Because those internal classes are completely hidden, the package is free to organize, rename, merge, or just aggressively refactor its internals as much as it wants. But on the outside, strict external discipline. This means other packages in the broader system are absolutely forbidden from depending on those hidden internal classes. And you know what? This creates an incredibly powerful guardrail. We can tell the AI to just go wild modifying internal classes to fix a bug, knowing for a fact that it physically cannot break external callers.
Which brings us to Section 3, the public inbound surface, the front door.
So, you're probably wondering, if external packages can't touch those internal classes, how on earth do they actually communicate? Well, we call this front door the public inbound surface. It is the one and only legal entry point into the package. Now, this surface could be built out of facade classes, service interfaces, or just public methods, but the core rule is always identical. Callers must rely on the public API, not the underlying implementation. For instance, a caller must depend on orders.api and literally never on orders.internal. And if you're using something like Java, you can actually enforce this with an iron fist using the Java Platform Module system, simply by exporting the surface package and keeping everything else totally locked down.
Meanwhile, safely tucked behind that front door, the sub-packages and internal classes are really just implementation tools. Sure, they divide the package's main job into smaller, bite-sized responsibilities, but they are absolutely not public access points. It's super important not to confuse class-level visibility inside a package with the package-level architectural surface. Because these aren't part of the public contract, your AI can freely rename them, move them around, or replace them entirely. And it won't affect a single external caller, just as long as that public surface interface remains completely untouched.
Let's jump into Section 4, cross-package collaboration, keeping it simple.
Okay, let's talk about how this all builds into cross-package communication without instantly devolving into a tangled mess. In this design, packages collaborate directly by calling another package's inbound surface. But what's truly revolutionary here is what's missing. There are 0 mandatory outbound adapters required. None. A strictly traditional architecture might force you to write outbound interfaces and wrapper code for literally every single call to another package.
But think about it. If every package already exposes a highly stable, backward-compatible inbound surface, direct calls to that surface are totally safe. We basically get to skip all that unnecessary indirection and boilerplate wrapper code.
But hold on, just because we don't demand formal outbound interface classes doesn't mean it's a free-for-all. Documenting these outbound calls is absolutely crucial. Every single package needs to maintain a simple dependency note that lists exactly which other package surfaces it calls. This does two things. It keeps your dependencies explicit and visible to us humans, but more importantly, it creates a literal instruction service for your AI. You could just point the AI straight to this document so it knows precisely which external tools it's actually allowed to use.
All right, Section 5, Testing and Backward Compatibility, the safety net.
Now that our boundaries are locked in, how do we make sure our system doesn't just shatter when we, or our AI sidekicks, start evolving the code? Well, because other packages depend on the inbound surface, that surface is your ultimate compatibility contract. It has to use what we call additive evolution, meaning you avoid breaking changes at all costs. We're talking about things like removing or renaming a surface method, tweaking parameter or return types, subtly shifting the meaning of existing behavior, or even sneaking in stricter validation that might trip up existing callers. If the AI knows it absolutely cannot make these specific changes to the surface, your existing callers are going to remain perfectly stable.
To actually enforce this, the architecture relies on a rock-solid two-tier testing model. Tier 1. Internal unit tests. These test the hidden internal classes and workflows directly, really just to build confidence inside the package itself. But the real magic, the actual safety net, is Tier 2. Surface functional tests. These tests treat the entire package as a total black box. They only hit the inbound surface to verify the external behavior contract. And here is the golden rule, folks. If an internal refactor by your AI breaks a surface functional test, the AI just violated the externally visible contract. Period. The change has to be rejected.
And finally, Section 6, the ultimate AI advantage, precision.
Okay, we've finally arrived at the payoff. This is how all these strict rules translate into absolute AI coding superpowers. It's amazing how we can take highly risky, broad AI prompts and transform them into perfectly scoped, laser-focused instructions. For instance, consider a vague prompt like, "Fix the bug in the order processing workflow." That is super dangerous. The AI might try to rewrite the public API, mess with external callers, or just shatter dependencies. Now compare that to the precise prompt our architecture enables. Update the calculation in orders.internal. Do not change orders.api. See the difference? That right there guarantees system stability. We've essentially handed the AI a sandbox where it can do its thing, but it literally cannot break the rest of the application. So, to quickly summarize this massive AI payoff, first, the package boundary strictly limits the scope of the AI's changes. Second, your stable inbound surface aggressively protects backward compatibility, keeping the rest of your system safe. Third, your simple dependency documentation dictates exactly what external calls the AI is permitted to make. The end result? You get a system where AI can make rapid, incredibly useful internal changes, all while your overall architecture remains completely unshakable. It's just a brilliant, disciplined approach that turns architectural intent into hard AI guardrails.
As we wrap up this explainer, I really want to leave you with a thought to chew on regarding your own software projects. Take a hard look at your current architecture. Are your package boundaries strong enough to safely unleash AI in your codebase? Or is everything sort of tangled together, just waiting for an automated assistant to pull the wrong thread and unravel the whole thing? Definitely something to think about before you let AI write your next major feature. Thanks so much for joining me today, and keep building with intention.